Now let's discuss about the biological responses to biomaterials. The first is coagulation cascade and coagulation response to biological material that are directly in contact with the blood. So biomaterials in the current use, the example is many medical devices involve polymeric biomaterials. For example, catheters, coating for pacemaker leads, and contact lenses are made of polymers. And the common mode of failure in modern biomaterials are in two aspects. That's the first, the biomaterials that directly contact the blood or non-blood contact. So materials that contact blood will form of blood clots. That will be common problem and issue. And materials for non-blood contact will experience so-called a foreign body response that isolates the device from the rest of the body. So these are the example of polymer biomaterials, which is these polymers for cataract, polymer lens for cataract surgery, and these are catheters. So as a good example for biological response to biomaterial, as first as a vascular graft, which is artificial vessel. One good example is a Dacron and PTFE or Teflon is the most widely used for vascular graft. Currently, only large diameter vessels can be replaced with these synthetic grafts, because the problem is when this diameter is smaller grafts, they inevitably lead to clotting and vessel failure, and we see why. So this is still a major issue which hasn't been resolved yet. So how does this happen for vascular graft is showing here. So we have, let's say, the cells isolated and expanded to put it into a scaffold, which is shaped as a vascular vessel. So the cells grow here and then secrete extracellular matrix. So these cells are not the same patient. So we grow these and then we have to go to decellularization. So acellular, but only remaining extracellular matrix proteins, and we ship it and we can use it as a bioengineered vascular grafts. So these are the examples. So this is like 8 centimeter long and inner diameter is about 3 millimeter. So vascular bypass is to reconnect blood vessels. These are example. The problem of example is so the vessels are suffering from ischemia by atherosclerosis. So we want to replace it by vascular bypass. Good example is coronary artery bypass graft, or CABG we call in short. Or there are people who has let's say lower extremities in the legs, peripheral vascular disease such as varicose veins, and those can be replaced by vascular bypass. So I bring some example as scaffold-based tissue-engineered vascular graft, or TEVG, manufacturing process here. So the cells are extracted from patient and isolated so that these cells can be used for graft. So it's autologous. And the cells are expanded in culture, and it can be either mixed with a polymer scaffold directly, or these cells can be seeded to pre-made polymer processed porous scaffold. And these constructs can be matured in a bioreactor to become a tissue-engineered vascular graft. So how can we, in terms of research aspect, compare this with our natural vascular graft, which is used using our own veins in a saphenous vein. So I put a picture here. So the patient's own saphenous vein, and these big and small veins have been used a lot for coronary artery bypass graft. And so we can compare this with this tissue engineered vascular graft. So these data is interesting to see. So we call coronary artery bypass graft CABG, but the saphenous vein is a field circle, and PTFE engineered ones are empty circle, which goes down over the years. You can see that graft patterns is deteriorating, and the other femoral pop above knee, and this filled and unfilled rectangles. You can see this, and it's not too bad. It's a little worse. And another femoral distant artery, and this one also, this triangles, still it's lower. So we can see still this patency rate for small diameter vascular bypass procedures. It probably is still better to use saphenous vein instead of this PTFE tissue engineered conduits.